Right now, on a tropical island off the southern coast of China, a rocket is sitting on a launch pad with a spacecraft bolted to the top of it that weighs more than 8 tons. The island is Hainan. The facility is the Wenchang Space Launch Site. The rocket is a Long March 5, the heaviest launcher China currently flies, and the thing riding on top of it is called Chang'e 7, a machine designed to land closer to the south pole of the moon than any spacecraft in history has ever attempted. The spacecraft arrived at Wenchang in April of 2026. It has been sitting there for months, going through integration, testing, fueling, and the slow grinding sequence of checks that precedes any deep space launch. Chinese officials have said publicly only that the launch will happen in the second half of 2026. Independent launch observers, watching airspace closures and shipping notices around Hainan, have identified a possible window much sooner than that, which means that by the time you finish watching this video, that rocket may already be gone. And here's the thing almost nobody says out loud when this mission gets discussed. There is no Chinese moon base, not a partial one, not a small one, not a prototype sitting under a dome at the lunar south pole waiting to be expanded. Nothing has been built. Not 1 gram of construction material has been delivered to the lunar surface by China or by anyone else. What actually exists today is a plan, a coalition of partner countries, a set of robotic missions, and a rocket for carrying humans that has never once flown to orbit. That gap between the headlines and the hardware is the entire story. Because the plan is real, the funding is real. The engineering progress over the past 36 months has been genuinely serious. And in several specific areas, China is now ahead of the United States in ways that are uncomfortable for Washington to acknowledge. But the base itself is a decade away at minimum, and the timeline has already slipped more than once in ways that most coverage quietly ignores. So let's go through what is actually happening. Not the artist renderings, not the announcements. The hardware, the dates, the slips, and the physics that makes all of this so much harder than it looks. Start with the spacecraft on the pad. Chang'e 7 is not a single machine. It is 4 machines flying as one stack. There's an orbiter, which stays in lunar orbit and performs remote sensing of the surface from above. There's a lander, which carries the whole surface package down. There's a rover, which drives across the terrain once it arrives. And there is a 4th element, the one that makes this mission genuinely unusual, which is a small rocket-propelled hopping probe designed to leap into terrain that no wheeled vehicle could ever reach. The full stack has a launch mass of around 8,200 kilograms. Originally, the design was described as 5-in-1. It included a small dedicated relay satellite alongside the other 4 elements. That relay satellite has since been removed, and the configuration is now described as 4-in-1. The reason is straightforward. In March of 2024, China launched a relay satellite called Queqiao-2 into an elliptical lunar orbit specifically to provide a communications relay for the 4th phase of its lunar exploration program. Queqiao-2 already supported the Chang'e 6 Farside sample return mission in 2024, and it is still up there, still working. So the relay hardware Chang'e 7 would have carried became redundant, and the mass budget got spent on something more useful. The landing target is where this mission stops being routine. Chang'e 7 is aimed at a peak near the southeastern ridge of Shackleton Crater at roughly 88.8 degrees south latitude. To put that in context, the Apollo landings all took place within a narrow band around the lunar equator. Chandrayaan-3, India's successful lander, touched down at around 69 degrees south in 2023, which was itself a record at the time. Chang'e 7 is targeting a point that is almost 20 degrees further south than that, in terrain that has defeated multiple previous lander concepts before they ever left the drawing board. The reason everyone is fighting over this specific patch of ground comes down to 2 words that get repeated constantly and explained almost never. Water ice. The moon has no atmosphere and almost no axial tilt. Its rotation axis is tipped only about 1.5 degrees relative to its orbit around the sun. On Earth, our 23-degree tilt is what produces seasons, and it is also why the sun rises and sets everywhere on the planet at some point in the year. On the moon, that barely happens. Near the poles, the sun never climbs high above the horizon. It grazes along the rim and it stays there. That produces 2 extraordinary consequences, and they sit right next to each other geographically. The first is that certain elevated ridges and crater rims near the pole are in sunlight for the overwhelming majority of the lunar year. These are sometimes called peaks of eternal light. They are not literally in permanent sunlight, but some of them receive illumination for 80 or 90% of the time, which for a solar-powered outpost is transformative. The second consequence is the inverse. Deep inside craters near the pole, there are floors that the sun has not touched in billions of years. No sunlight has reached them since roughly the time the moon formed its current orientation. And with no atmosphere to move heat around, those floors are not merely cold, they are among the coldest measured places anywhere in the solar system, with temperatures dropping below 100 Kelvin, which is colder than the surface of Pluto. Those are called cold traps, and they are the reason this entire race exists. Over billions of years, comets and asteroids have delivered water to the moon in impacts. Almost all of it flashed straight to vapor and escaped into space, but a small fraction of those molecules migrated across the surface, drifted into these permanently shadowed regions, hit that extreme cold, and froze. And because nothing there ever warms up, the ice never left. Orbital measurements from multiple missions over the past 2 decades have found strong signatures of hydrogen concentrated in exactly these regions, which is the fingerprint of buried water ice. What nobody knows is the thing that actually matters. How much is there? What form is it in? And can it be extracted? Is it a sheet of solid ice you could mine with a drill, or is it a few percent of frost bonded to grains of regolith scattered through the top few meters of soil? Those 2 answers lead to 2 completely different futures. One of them means a lunar base can refuel itself, split water into hydrogen and oxygen for propellant, and generate breathable air and drinking water on site. The other means every kilogram of everything has to be shipped up from Earth forever, at costs that make permanent habitation economically absurd. Nobody has ever gone and looked from the ground. That is the entire mission profile of Chang'e 7, and this is where the hopping probe becomes the most interesting piece of hardware on the vehicle. A rover cannot go into a permanently shadowed crater floor. It is a solar-powered machine being asked to drive into a place that has no sunlight, down slopes that are frequently steep and littered with boulders, into temperatures that will freeze its lubricants, crack its seals, and kill its batteries within hours. Every rover ever built would die in there. So the solution is to not drive. The hopper is a small, rocket-propelled scout that separates from the lander, flies over the terrain, descends into the shadowed region, takes its measurements during a brief window, and either flies back out or accepts that it is a one-way trip. It carries cameras and instruments intended to analyze the local environment directly. It is designed to reach regions that no rover can access. And if it works, it will produce the first ground truth measurements ever taken inside a lunar cold trap. That is a genuinely difficult engineering problem, and it is worth understanding why. The hopper has to navigate autonomously in darkness over terrain that has never been mapped at high resolution because you cannot photograph what is not lit. It has to manage its own thermal budget in an environment that will pull heat out of it faster than almost anywhere else in the solar system. It has to do all of this on stored power, with no ability to recharge while it is down there, and with communications that are constrained by a line of sight to the relay satellite. There is no margin for a slow, careful approach. It goes in, it works, and it either survives or it does not. Chang'e 7 also has to survive something that every South Polar mission has to survive, which is the terrain itself. The lunar South Pole is not the smooth gray plain of the Apollo footage. It is old, heavily cratered, steeply undulating ground with long shadows that make optical navigation extremely difficult because a shadow and a hole look identical to a descending spacecraft. The landing technology on Chang'e 7 includes navigation improvements built specifically for this problem, using landmark image recognition to work out where the spacecraft actually is, against terrain that offers very little reliable visual reference. Kikyao 2 solves the communications problem for the mission. It does not solve the thermal problem, it does not solve the terrain problem, and it does not solve the landing problem. Those are still open, and they will remain open until the moment the lander is on the surface and reporting. Now, the part that most coverage skips entirely, the schedule. Chang'e 7 was not always a 2026 mission. Under China's earlier planning, it was scheduled to launch as early as 2023, ahead of Chang'e 6, the Farside sample return mission that eventually flew in May of 2024 and became one of the most celebrated planetary science achievements of the decade. Chang'e 7 got reordered, redesigned, and pushed back, and its departure eventually landed in the second half of 2026. That is a slip of roughly 3 years on a flagship mission. The same thing has happened downstream. Chang'e 8, the follow-on mission and the one that actually starts laying groundwork for a base, was for years described publicly as a 2028 mission. Chinese officials repeated that date consistently across multiple international presentations. More recent scheduling now places it around 2029. Some of that is normal program evolution. Some of it is manifest pressure because the Long March 5 flies at a relatively low cadence, and its launches are shared across Chang'e 7, the Tianwen 3 Mars sample return mission, and other high-priority payloads. There are only so many of these rockets, and they cannot all fly at once. This matters because schedules are the honest metric in spaceflight. Any agency can announce a goal. And what tells you whether a program is real is whether the dates hold and whether the hardware appears when it was promised. On that measure, China's sequence is split into 2 phases. The first phase aims to complete a basic version of the station by around 2035, concentrated in the lunar South Pole region. The second phase aims to upgrade that basic version into an expanded configuration by around 2045, and to extend it beyond the pole into a network connecting the South Pole, the equator, and the far side of the moon. Sit with those dates for a second. 2035 for a basic station, 2045 for the expanded version. That is not next year, and it is not a surprise announcement waiting to drop. That is a program on a 20-year horizon, being built one robotic mission at a time, and Chang'e 7 sitting on that pad in Hainan right now is step 1 of a sequence that has not yet reached step 2. The station is also not designed as a continuously crewed outpost, at least not in its basic form. It is described as an expandable, maintainable system capable of long-term robotic operation with short-term human participation, meaning it runs itself most of the time and people visit. That is a meaningfully different thing from a colony, and it is a much more realistic engineering target. Now, the hardest unsolved problem in the entire concept, and the one that determines whether any of this is possible at all: power. A lunar day and night cycle lasts roughly 29.5 Earth days. That means a station on the surface faces a night that lasts about 14 Earth days, during which solar panels generate nothing at all, and during which temperatures collapse. Batteries capable of carrying a full base through 14 days of darkness every month, indefinitely, would weigh more than anything anyone can currently deliver. Radioisotope generators do not scale to the power levels a base needs. Fuel cells need fuel, which brings you back to shipping mass from Earth. There's essentially one answer, and everyone building lunar plans has landed on the same one: nuclear fission. Preliminary plans for the ILRS include building a nuclear reactor on the lunar surface. That was shown publicly in a presentation by Pei Zhaoyu, the chief engineer for the Chang'e 8 mission, which also indicated that the base's energy supply could depend in part on large-scale solar arrays built on the surface. So the architecture is likely hybrid. Solar, where sunlight is reliable, on those high illuminated ridges, with fission carrying the load through darkness and powering anything energy-intensive like resource extraction. And here is where the Russian side of this partnership stops looking symbolic and starts looking strategic. Wu Weiren, the chief designer of China's lunar exploration program, has said directly that power supply is a key open question for the ILRS, and that in this area, Russia has a natural advantage. His assessment was blunt. On nuclear power plants, particularly on sending them into space, Russia leads the world, and it is ahead of the United States. That claim is not propaganda. The Soviet Union launched more than 30 satellites carrying fission reactors during the Cold War, developing operational experience with space nuclear systems that nobody else accumulated. The United States, by comparison, has flown exactly one reactor in space, a satellite called SNAP-10A launched in 1965, which operated for 43 days before it shut down and has been dead in orbit ever since. 60 years later, that is still the entire American flight record for nuclear fission in space. So the partnership makes sense on paper. China brings launch capability, spacecraft, funding, and industrial capacity. Russia brings decades of space nuclear engineering that China does not have and cannot quickly replicate. Whether Russia can actually deliver is a completely separate question. The Russian space program has been contracting for years. Luna 25, its first lunar mission in almost half a century, crashed into the moon in 2023. Its budget, its industrial base, and its access to Western components have all been severely damaged since 2022. The Yenisei Super Heavy rocket that was supposed to be Russia's contribution to ILRS construction exists mostly as a design study. Analysts looking at this partnership tend to describe it in similar terms. Russia has older but proven nuclear technology. China has newer but unproven approaches, and the combination could work, but only if the Russian side survives long enough to contribute. That uncertainty is why the coalition around ILRS has been growing so aggressively, and why the international payload capacity on these missions matters more than it might appear. China has framed the ILRS as an explicitly open international project. The stated ambition is described as the 555 project, which aims to bring in 50 countries, 500 international research institutions, and 5,000 overseas researchers. The current membership list includes Russia, Pakistan, Belarus, Azerbaijan, Egypt, South Africa, Venezuela, Thailand, Serbia, Nicaragua, Kazakhstan, and Senegal, along with a number of research institutions and organizations. Look carefully at that list, because it tells you what this coalition actually is. With the exception of Russia, almost none of these countries has independent launch capability or the industrial base to contribute major hardware. They are not building the station. What they are contributing is instruments, scientists, ground station access in useful geographic locations, and most importantly, political alignment. That is not a criticism, and it is not a weakness. It is a strategy, and it is a deliberately different one from the American approach. For a country with an emerging space sector, joining ILRS means your instrument flies to the moon, your engineers work alongside a major space agency, your universities get data, and your national program gets a genuine milestone at a fraction of what an independent mission would cost. Egypt, for example, has an AI-enabled camera developed for the Chang'e 7 mission, tested with support from a Chinese optics institute. Pakistan, France, Italy, and the European Space Agency all had payloads operating on Chang'e 6. That is soft power executed through hardware, and over 20 years it builds a block. Meanwhile, running on a completely separate track is the part of the program that gets conflated with the base constantly and should not be: the crewed lunar landing. China has publicly committed to landing astronauts on the moon before 2030. That is a different program, with different hardware, different management, and different objectives from the ILRS robotic missions. It is not the base. A crewed landing is a visit. The base is infrastructure. They will eventually converge, but right now they are two parallel efforts with separate schedules. The crewed architecture requires 4 major new pieces of hardware, and all of them are real, and all of them have been tested, and none of them has flown to orbit. There's the Long March 10th, a new heavy-lift rocket built specifically for this mission. It uses a 3.5 stage configuration, stands around 90 meters tall, and is a genuinely different vehicle from anything China currently flies. There's Mengzhou, the crew spacecraft, whose name translates roughly as Dream Vessel. There's Lanyu, the 2-person lunar lander, whose name comes from a line in a Mao Zedong poem about embracing the moon. And there is the supporting equipment, including the Wangyu lunar spacesuit and a crewed lunar rover. The mission profile is worth understanding because it is different from Apollo and different from what NASA is currently attempting. 2 separate Long March 10th launches are required for a single landing. One launch sends the Lanyu lander to lunar orbit uncrewed. A second launch sends the Mengzhou spacecraft with the crew aboard. The 2 dock in lunar orbit. 2 astronauts transfer across into the lander, descend to the surface, conduct their operations, and then the lander carries them back up to lunar orbit to rejoin Mengzhou for the trip home. That architecture is conservative. It does not require orbital refueling, it does not require a space station in lunar orbit, and it does not require any technology that has not been demonstrated in some form. It is roughly Apollo's approach, executed with modern hardware and split across 2 launches because China does not have a Saturn V equivalent. Conservative architectures have a habit of working. The test campaign over the past 2 years has been methodical, and it is the strongest evidence that this program is serious rather than aspirational. There have been tethered ignition tests of the Long March 10 first stage, holding the rocket down while its engines fire. There was a zero-altitude abort test of the Mengzhou spacecraft, verifying that the escape system can pull the crew capsule clear of a failure on the pad. In August of 2025, an integrated landing and takeoff test of the Lanyu lander was carried out at a test facility in Hebei province, the same kind of site used years earlier to validate the Tianwen-1 Mars lander. Those tests verified the landing and takeoff systems, the control systems, the shutdown procedures on lunar contact, and the compatibility between guidance, navigation, control, and propulsion. Then on the 11th of February 2026 came the most significant test so far. At Wenchang, China conducted a low-altitude demonstration and verification flight of the Long March 10th, in which a Mengzhou spacecraft lifted off on the ignition of the rocket's core first stage as part of a maximum dynamic pressure abort test. Both vehicles were in prototype configurations. It was the first low-altitude flight test of the Long March 10th, and it validated the escape system at the worst moment of a real ascent, the point of maximum aerodynamic stress. Chinese officials have stated that the Long March 10, Mengzhou, Lanyue, the Wangyu suit, and the crew rover have all completed the main work of the prototype stage. In May of 2026, the program announced a structural change, integrating the robotic Chang'e activities and the human spaceflight effort into a single unified lunar exploration program, with the next key milestones named as technical verification flights of the Long March 10 and maiden flights of Mengzhou and Lanyue. So here's the honest scoreboard. The tests are real, and they have gone well. The hardware exists in prototype form, and the Long March 10 has still never reached orbit. Mengzhou has never flown a full mission, and Lanyue has never been anywhere near the moon. Between where the program is now and a crewed landing before 2030 sits an uncrewed orbital test campaign that has not yet started, which is where the other side of this race comes in, because the American program has spent the same period going through a fairly dramatic reorganization of its own. In March of 2026, NASA announced that the Lunar Gateway, the small space station intended to orbit the moon and serve as a staging point for Artemis missions, is officially paused, and that a lunar surface base will be built instead. That is a significant shift, it supporting astronaut operations. And in August of 2026, NASA's leadership announced plans to place a nuclear fission reactor on the lunar surface by 2030, targeting around 100 kilowatts of electrical output. The framing was unusually direct. NASA's interim administrator Sean Duffy said publicly that the United States is in a race to the moon with China that